Hi, this is Patrick at StopSprayingUs.com, and on the phone, or actually Skype with us today, we have Mick West from Metabunk. And hey, Mick, why don't you explain what Metabunk is, how you came to do it, and
All
that
right.
stuff.
Yeah. Well, I am a retired video game programmer. I worked on the game Tony Hawk's Pro Skater about 10 years ago, and I retired and just kind of doing some part-time work since then, and I have a lot of spare time, and so I've just been following up on things I find personally interesting to me, and I've always been interested in things like UFOs and things like that, and strange topics, and so I tend to argue with people on the internet about things like that, and I ended up just setting up my own site to do that. I started with a site called Contrail Science, which I think that I started around 10 years ago, which was talking about the chemtrail theory, which I'm sure you're familiar with.
Certainly have.
And and then I kind of branched out into Metabunk, where I talk about a whole bunch of other like conspiracy type things, like 9/11 things, uh, things like people who think that Sandy Hook was fake, people who think the Earth is flat. I do a whole variety of things, but I kind of started out doing the whole chemtrail thing, and so I still do quite a bit of that. We do a lot of stuff like identifying planes and flying objects and stuff. It's kind of interesting stuff. Nobody pays me to do it. It's just something I do by myself. I made enough money on the with the video games, and it's just kind of I do it as a hobby.
Yeah, and you live in California now, don't you?
I do, yes. I'm over by Sacramento.
Yeah, very nice, very cool. So anyway, as people, whoever knows me, I've been talking about chemtrails and for some time, and I thought it would be really useful for people to hear the other side because anyone who is in one group will only hear one thing, and the same for the other side. So I thought I'd have a chat with Mick to explain how he sees the
Yeah.
chemtrail contrail conspiracy theory, and I have a few questions. And it'll be like thing. Actually, let's start off with first of all, what is a contrail or what is a chemtrail?
Well, first of all, I just want to say, thank you for doing this type of thing because I think there is a lot of polarization
Yeah,
between
unnecessary.
groups where people they just don't listen to what they perceive as being the other side. Like people will think that I'm anything I say is a lie, so they just won't listen to it. And I've got a lot of information on my website that is all well referenced, and you can verify it for yourself. It's not just me saying something. But to your question, a contrail is a condensation trail. It's actually a type of cloud. It's really essentially the same as a regular cloud, like a cirrus cloud, a high altitude cloud, and it's formed when the water in the aircraft engine exhaust mixes with the ambient air and basically triggers the formation of a cloud. It's not actually a cloud formed from the water in the exhaust. That just actually triggers the formation of the cloud. And there's two types of contrail. There's exhaust contrail, which is what, as I just described, and then there's another type which has led to a lot of confusion, which is the aerodynamic contrail, which forms over the entire surface of the wing. And it looks a bit different close up. It's more like a flat ribbon than a couple of streams coming out of the engine, and it can form at lower altitudes and in a wider range of conditions.
And
That's
what's that one called? What's that one called again?
an aerodynamic
Aerodynamic.
contrail.
So
Yeah.
is this related to, like, for example, like Hong Kong is humid and hot, and
Mm-hmm.
whenever planes land there, you'll see wingtip vortices coming off the side. Is it similar to that?
It is similar to that. Yeah, what it is, it's a reduction in the air pressure. When you have a vortex, obviously the air is spinning around very rapidly, and that forces the air to the outside. So the pressure in the middle of a vortex is lower than the pressure outside. And
Okay.
you may have seen like science experiments on TV where people say like make a cloud in a bottle, and they do it by pumping air into a bottle and then opening it quickly. When you open a beer bottle, you see a tiny little bit of like a cloud basically in the neck of the beer bottle. That's the same type of thing. The pressure is being suddenly lowered, which means the air is expands, and so it's unable to hold the same amount of moisture, and so it basically a cloud just kind of springs into existence because the conditions make it impossible for the water to stay in its gas form. So
Well,
yeah,
that's the same way. Like when wet air goes up a mountain, it turns into a cloud because there's lower pressure.
essentially yes. Essentially, it's
Right.
it's kind of
But
different because of the way the air is moving from one place to another with in that instance, whereas in this instance the pressure is being lowered in the same place, so it's slightly
so
different. But
I'm not sure if you mentioned, or maybe I misremembered. So there's with uh,
the aerodynamic
these
trails,
the aerodynamic ones that go the full length of the wing. Isn't there some chromatic effect in there as well?
yes,
How does that happen?
it happens because of the uh, the way they've
Oh, chromatic,
formed.
by the way, for listeners, that's like
Yeah,
you
just
can see some colors in there.
colored basically. It's a kind of a rainbow effect, but if you look at it, it's not actually the same spectrum as a rainbow. It's a different type of spectrum. It's a thing called Mie scattering, MIE scattering, and it's to do with the size of the particles. When the cloud is forming, they start out as being microscopic, tiny little nano size particles of water, and then they grow in the air as more and more water gets attracted to the existing water drops. So you start out with very, very small particles, and then they become a bit larger as you get further back. So as you get further away from the plane, the particles are going to be a bit bigger. And the size of the particle affects the way it interacts with light, because they're a similar size to the wavelength of the light. And so the different sizes scatter different colors of light, and so you get this spectrum of light behind the planes. It can look quite pretty. Some of them are very nice looking. From the ground, they kind of look washed out, but you might have seen some other photographs taken from higher up. If it's taken from another plane, the sky kind of looks black, and you get these very dramatic colors in the trail. And at that point, it's actually water vapor. You think of contrails normally as being ice, and you sometimes get like a halo effect in a regular ice contrail. But when an aerodynamic contrail is forming, it actually starts out as tiny spherical water droplets, and it gives this
Uh,
very, very nice effect.
so these are mostly lower altitude and higher humidity.
Well, this is another thing with these aerodynamic contrails. The ones that you see that persist up in the air are actually pretty high altitude still. They're in the like 15 to 25,000 feet range. And now regular contrails form generally higher than that, 25 to 40,000 feet or 40,000 plus. Like by regular, I mean exhaust contrails, which are the more common contrails. So you do get these exhaust contrails at pretty high altitude. I see them here, like at Sacramento, a lot because the traffic that's climbing out of San Francisco that's heading eastbound is climbing through around that range, 20 to 25, 30,000 feet over my house here. So I
Okay.
see these aerodynamic contrails a lot more than many people would see them. You probably would not see them being in San Francisco. Uh,
I sometimes.
yeah,
I mean, what I just call them like
you
like
you do a
wing sprayers. I call them
right.
because it looks like there's trail coming from the
Yeah,
entire
yeah, and
length of the wing.
there's a few videos as well, like pretty famous videos put forth by chemtrail people like Dane Wigington. I think is always saying, we have absolute proof of chemtrails because he puts out these videos of aerodynamic contrails, and I think he has been quite resistant to the explanation that they're aerodynamic contrails, but that's what they are. But my point, real quick, about not seeing them over San Francisco is that you see them most commonly where planes are climbing. It's quite rare to see them when a plane's at cruising altitude because normally they just form exhaust contrails, and so the exhaust contrails tend to just kind of blot out any aerodynamic ones you see. But you do see them occasionally, as you know.
Okay. So persistent contrails, they are becoming more common. Would you agree or disagree?
I would disagree. I think Well, it depends what you mean by more common. There is more air traffic now than there was in the 80s, so obviously there's a lot more persistent contrails now because simply because there's more air traffic. There is there are actually some increases, and I think what you were suggesting is that the conditions are changing, so that there's more contrails, or there's saying something added to the jet fuel or something like that. But really, there's a few other reasons why you see more. One of those reasons is something called the reduced vertical separation minima, which is the minimum distance, the minimum vertical distance that planes can fly, the distance between them vertically, which used to be 2,000 feet. And in, I believe, the 2000s, it was changed to 1,000 feet, which meant that a lot more air traffic could be fit into the same airspace. So it gave it a much more denser packing of planes, and that allowed more planes to fly at cruising altitude. And it opened up the door for things like small local commercial jets. So there's changes in the types of air traffic. Like you get you can fly, for example, from Sacramento to Medford. Medford in the southern Oregon. I've flown there. Well, have I flown there? No, I haven't flown there. I know people who have flown there. Actually, no, I have flown there, but I flew there from LA. But you can actually fly there from Sacramento. Like it's actually no, you can't. Sorry, I'm getting a bit confused here. You can fly to Medford from Los
SFO.
Angeles. Yeah,
I think SFO as well. Yeah.
yeah. You can't fly from Sacramento. Most people will drive. But that's the type of route that didn't exist 20 years ago, because people would generally fly to hub cities and then fly to these other cities. So you have an increase in the number of routes. So let's say there is a new route between, say, Sacramento and Medford. The people between Sacramento and Medford might see planes where they weren't seeing them before. Because the traffic was normally further over to the west, because it's from San Francisco and LA.
So in other words, more planes, more trails.
More planes. There's more routes. There's more high flying planes because of these smaller commuter jets. So they just kind of jump up and then jump down, but they're still flying at high altitude. And there was one other reason, but I can't remember it off the top of my head. But yeah, there's a few other reasons. But the atmosphere hasn't really changed in a way that creates more contrails. The other thing is high bypass engines, high bypass turbofans. Now, this is something that kind of gets presented backwards. High bypass jet engines, which are the modern types of engines with the very big fans on the front, they are much more efficient than the older engines, which had a smaller fan on the front, because they convert a lot of the energy of the jet engine, the jet turbine, into turning this fan to produce thrust rather than just shooting the hot gases out of the back. So this actually cools down the exhaust of the high bypass turbofans, and so the exhaust that's coming out when it mixes with the air is a little bit cooler, and so it gets to the condensation point quicker, and so it's actually a bit more likely to create a contrail than the older engines. So new engines actually are more contrail friendly in a way than older engines. It's not a huge amount. It changes the range in which the temperature range. If you can think of the atmosphere as being like divided into slices, into layers, there's a layer at which the conditions are right for contrails, and it expands that range by a few hundred feet. So it does actually create a few more contrails than the older engines.
Okay, cool. So going back to the term contrail, condensation. Condensation. Don't you need 100% humidity for something to condense?
You do, yes, and
Relative humidity, that is.
you do, and that's where the moisture in the jet exhaust comes in. When you burn something, you're burning a hydrocarbon, which is hydrogen and carbon. You're burning it in oxygen, which is just oxygen O. So the hydrogen combines with the oxygen, and the carbon combines with the oxygen. So you end up with carbon dioxide, which is carbon and oxygen, and hydrogen and oxygen, which is H2O, which is water. So what comes out of the back of a jet engine is 4 parts carbon dioxide and 1 part water. It's just an awful lot of water. When you burn a gallon of jet fuel, you're actually creating about 1.3 gallons of water. And so when you add this water to the air outside the plane, there's a brief period where the humidity goes over 100%. So if the humidity outside is, say, 60 or 70%, that's very cold air. You mix it with this hot, humid gas that's coming out, and there's a brief period when the humidity rises over 100%, and at that point you get condensation of water, liquid water.
But then, surely, like right now, I have some tea here. If I spilled that tea, it would evaporate. It wouldn't. I mean, my cup wouldn't overflow because it's not 100% humidity here.
Yeah. Well, so what happens next in the Contrail formation is the magic temperature of minus 40 degrees, which is magic in a couple of ways. One is that minus 40 degrees is the same in Fahrenheit and Celsius. Minus 40 C is minus 40 F, which confuses some people, but you could check it, it's true. And minus 40 degrees is what's called the homogeneous freezing temperature of water, which means the temperature at which water will freeze without anything being added to it. Now, when water freezes normally, it needs to freeze on something. It needs some kind of nucleus, some kind of nucleation site. So you've probably seen little experiments where you take a bottle of water, stick it in the freezer, and you take it out and it's still liquid, and then you bang it on something and you see it freeze. Yeah, that's because it gets disturbed and nucleation sites form. Or you could do something like put a bit of salt in it, and hello, you still there?
I'm still here. Yeah, can you hear me?
Yeah. You've suddenly gone very quiet. So
sorry about that. Hang on. I'll bring the. Can you hear?
All right, I can hear you now. So okay.
Sorry, it's again. I'm using the. I mean, the recording will sound good because I'm using my microphone. It's just the. This is the laptop's built-in microphone. Which is
all right. So
sorry about
that. Let's see.
So actually, do you want to restart your?
Yeah.
Thing, so edit this a little bit out. Yeah.
I was talking about ice, and the minus 40 degrees is the homogeneous nucleation. Actually, homogeneous ice nucleation. It's the temperature at which water will just freeze without having to add things to it. Right. So, what's happening when you say on a cold day when you breathe out, you see a little cloud, and this is comprised of liquid water droplets. Like most clouds at low altitude are comprised of liquid water. It's just trillions of very, very small droplets of water in suspension, and that little cloud will evaporate very quickly, even on a fairly cold day. But if the temperature is lower than minus 40, then those tiny little droplets of water, which are pure water, will just freeze by themselves. Now, normally, they wouldn't freeze because they're pure water and they're not touching anything. But because it gets below this magic temperature of minus 40, the homogeneous ice nucleation temperature, they freeze by themselves and they turn into ice. And ice has a different humidity at which it will persist than water. So when it freezes, that kind of locks in the contrail. There's two types of relative humidity you may have seen. There's relative humidity with respect to water, and there's relative humidity with respect to ice. And you can convert one to the other, and it turns out that the relative humidity with respect to ice is 100%, when the relative humidity with respect to water is only around like 60 or 70%, or sometimes even lower. It depends on the temperature. So you can have a clear sky with no clouds in it, and if you were to put a water cloud into that, it would evaporate. But if it's cold enough, that water cloud will freeze into an ice cloud, and then the humidity, being like 60 or 70%, is then high enough for that ice cloud to persist. And that's what happens with contrails, with the exhaust contrails. It's a bit different for aerodynamic, but It's
So,
similar physics.
so you're saying that at -40, you do not need a condensation nucleus.
That is correct. Yes, you do not need a
Right.
condensation nucleus for freezing. Sorry, you do need a well, you don't really need a condensation nucleus. There's some complications here because there's ice condensation nuclei and there's water condensation nuclei, which are different things. If there were ice condensation nuclei in the air, you would actually get a cloud. But ice requires a very specific type of molecular structure on which to condense. Water is much less picky. Water will condense on just about anything. And there's always water condensation nuclei in the air, which is why you see clouds all the time. Every time you see like a cloud up in the air, it's formed because it's forming on basically things like mineral dust and salt and sulfur particles and things like that, which are in the air normally because they act as water condensation nuclei. Now, ice clouds, they're a bit different. They're a little harder to form. So when the plane is shooting things out the back, it's the water forms on water condensation nuclei. The ice requires that water to freeze, and it won't form if it doesn't freeze. So you need that kind of magic temperature of -40.
Okay. And so once the plane's gone away, the temperature, the super humidity that was in the exhaust of the plane is long gone. It gets back to, normal, stable.
Right.
Um, shouldn't then ice cube, if you leave an ice cube out, it'll lose ice. It'll
Well, if you,
like the,
but the thing is,
if you leave it in the sun, I mean, yeah, it can melt, but if you keep it cold, if you keep it below freezing, it will still reduce. Ice will, the
it will,
mass will come
it will,
off.
yeah,
So how in a situation where it is less than,
less than
100%
100.
100% RHI, how could that crystal grow and spread?
Well, the thing is, it wouldn't if it was below 100% RHI. It can if it's below 100% RHW. It needs to have higher than 100% relative humidity with respect to ice, and that is something around 50 to 70% of relative humidity with respect to water, which is the normal thing that you see measured. But yeah, it does need 100. So if you see a contrail that was existing in conditions that you know to have low humidity with respect to ice, then that would obviously be something that's very suspicious. But the problem there is that it's very difficult to know what the relative humidity of something is without actually going there and measuring it. Humidity can vary vastly from one parcel of air to the next. If you think about, like, say, clouds, the humidity in a cloud is over 100%. The humidity outside a cloud is below 100%. So it can vary in the distance from the inside to the outside of a cloud, and it's just the same in a clear blue sky. Even if you can't see it, those areas of humidity are still there. So you still get this variation in humidity. So you can't really easily tell what the humidity is by looking up at a plane, looking at a region of sky. There's no way really of other than the fact that contrails are forming. And contrails are actually one of the best indications of what the humidity is. Other than that, there's no easy way of telling what the humidity actually is, except in
So,
general.
sorry to jump in here. I'll play devil's advocate. Why not?
Okay.
There's plenty of videos where you see a plane and it'll look like it's leaving a dotted line.
Yeah.
Is that because would you say like these warm or wet or dry pockets are that close together?
Yeah, absolutely. I mean, that's what I was saying earlier with the clouds. If you look at, say, a cloudy sky that isn't 100% overcast, it's a patchy cloudy sky. Now, if you kind of imagine a plane flying through those clouds, and let's say it was some type of plane that was changing the color of the clouds, So whenever it flew through a cloud, it changed the color of the bit it flew through. So you could see these red lines or whatever as the plane flew through the cloud.
Mm.
That type of patchiness is still there when the clouds aren't there. So if you kind of imagine that same sky and take away these patchy clouds, and then have a plane fly through those areas, and wherever it flies through where one of the clouds used to be, it leaves a trail of cloud because it's triggering the formation of clouds in that region. Um, and that's why you see these breaks in the trails, because you've got variations in humidity usually, but humidity, relative humidity, but also in temperature. You see things like rising areas of convection and things like that, but it could just be just normal, basically ripples in the atmosphere.
Mm. Okay. Actually, ripples. Do you do anything about? I mean, sure, it's been brought up to you. There's. I look on NASA Worldview.
Mm-hmm.
I've been seeing um, a lot of what you would probably call gravity waves. Um, they look like basically like ripples, like when like in at low tide, when the sea goes back and forth, you have that sort of like ribbed pattern in on
Mm-hmm.
the sea.
Yeah.
And I know when you have two air masses going over each other, you have this ripple effect. I have I have seen increasingly uh, these ripples all over the place, but I've seen them in the same area with different wavelengths and different directions, multiple. I mean, maybe I could send you some pictures for that. Can that be explained by air masses?
Well, the atmosphere is essentially a fluid.
Of
Uh,
course.
so the principles of fluid mechanics apply to it, and it's the atmosphere is very tall. The atmosphere is going up to 7 miles or so, where clouds in a region where clouds form, and so there's regions of it moving in different directions. You could have the air at one altitude moving like northwest at 10 miles an hour, and then have it moving southeast 50 miles an hour, like a mile above that. So you can have all these different layers of the atmosphere that can do completely different things. So it's quite possible to get ripples in the air moving in one direction and ripples in the air moving in another direction. I think this is perhaps not entirely intuitive, because when we think of ripples, we think of ripples on the surface of things. Like you think of ripples on the surface of the water, uh, which is the most common idea of ripples that we have. But these are more three-dimensional ripples. They're not really on the surface of things. They're kind of at a level like between two air masses. But there's lots of different, essentially surfaces all the way up when you go through the atmosphere. So you could say there's the interface between like 10,000 feet and 12,000 feet, and then between 12,000 feet and 14,000 feet. So you can have all these completely different layers. So the fact that you get ripples in two directions doesn't really mean anything. And the
Well,
variations,
actually, several directions. I mean,
yeah.
I'll have like 8 or 9 directions in the same area, and they're different sizes. So this is very, very odd looking.
Yeah, but I'm talking about ones where they're overlapping each other, where you can see like
Oh yeah,
a
yeah, yeah.
crisscross
But
pattern. It would
yeah,
be,
there you go, like a crosshatch effect.
yeah, yes. You see two things. You see this in the ocean. There are actually there's a few places where you do actually see it on the surface of the ocean because of the way a bay forms. It's a lot harder to get in the ocean than in the atmosphere, but you can actually see these ripples actually at the same water level going over each other. It's pretty interesting. But yeah, you there's nothing to stop ripples forming in different directions, even over the same area, but certainly in the same region. The wind direction can be very chaotic, not only at different altitudes, but in fairly close proximity, within like a few tens or hundreds of miles. You're looking at satellite images. You're looking at pretty broad areas. Um, but yeah, I don't really see anything untoward there. And if you look at like older satellite images, they show up in those as well. I've got a great book called Spacious Skies by Richard Scorer and Arian Vercake. And it's got a whole bunch of satellite images from the 1980s, and they show things like this. And they're basically exactly the same now as they were before. Of course, now we've got Earth View, so you can spend all day looking at it. So you're
Oh,
gonna see a lot
quite
more.
often do. Oh,
Yeah.
here's a slight, maybe like a side note here. Do you know if there's a repository? Because like before, I think it's like 2011 or 2008, they mislaid their imagery. Did anyone else say that? Do you know?
Uh, the
Someone must have.
yeah, there are repositories of various satellites. I'm not
So, I
sure
mean,
how far back.
I do like the. I mean, the world views. It looks. It's way easier on the eye than like the radar-y ones and stuff. And it'd be. I think they had like some sort of the claim that they
Yeah.
had some sort of hard drive crash and they lost it and they didn't have a backup or something
Well,
ludicrous.
the
But whatever.
satellites, the Terra and Aqua satellites that they use,
Those ones.
they only go back that far. I'm not sure when they were actually launched. But yeah, I'm just looking at WorldView right now. I want to see how far
No,
back it
it
goes.
stops on January 1st, 2008, and I think if you go try to go back one day, it'll stop dead. But it used to be there, but it's not there
No,
anymore.
I'm seeing I'm back at 2003 now, so
Or oh,
I don't
huh,
know.
okay.
Maybe they fixed it. Uh,
Yay! Oh, anyway, well, that was a side note. Another satellite thing that I've seen are these very sharp-edged clouds that are becoming increasingly common, or at least they seem increasingly common to me. It just looks like they've been carved with a like very sharp knife. Some of them are dead straight, but other you know what I'm
yeah,
talking
no, I know
about.
what you're talking about.
So
Actually
how could those have come to be?
they're very transitory clouds. They don't last very often. The problem is like when you see them on Worldview, you're only getting one image a day, or you're getting two
Well, you're three actually,
with
because you got
Aqua.
Suomi, Aqua, and Terra.
Yeah, but you generally don't see very much development because they're so far apart in terms of time. I think they're like 2 hours
Well,
apart.
the Terra goes over first, and then Aqua and Suomi are pretty close to each other.
Right. Well, but the what we have now is the GOES 16 satellite, which was is not quite operational yet, but it does actually. There are viewers online. There's one called Slider. I think you can just probably Google for GOES
Yeah,
16
I just
Slider.
pulled it up. I'm looking at our series. Not sure if that's Slider.
I can send you a link to it.
Oh, cool.
But
Yeah, yeah.
it's basically a full disk view of the Earth, and it's updated every 15 minutes.
Oh,
So
nice. Oh, cool.
you can get animations of these clouds forming, and you can actually see contrails forming. Uh, yeah, so it's the Ramb Slider site. I'll just drop you a link.
Currently flying, launching soon. Cool. Let's check into that. Where's the pretty good thing? Oh, bingo. There you
So yeah, I just sent you a link to it, and if you click on that, it actually shows you a full disk version of not full disk image from a geostationary satellite, which is fairly high resolution. It's not as high
go. Oh,
resolution.
nice. Oh, that's cool.
Yeah, the site's a little clunky at the moment. Yeah, I find it best to like, zoom right in and then refresh so you can see what's going on. Like if you zoom in over California right now, you'll see some ripple clouds to the north of LA.
Huh?
Uh, and you'll see that
Controls to zoom
we
in.
are. Oh, wait, there's some
Is
ripple
it?
clouds. Yeah, you should be able to just double click to zoom in,
Okay.
and it'll tell
Oh,
you.
cool. All right.
And I would zoom in and then refresh the page when you get to where you want to go, because it's otherwise it messes up.
All right.
But yeah, this is a very good way of looking at how these clouds form. And to your point about square clouds, they
Well, no,
basically
no, not the square ones, but the ones that look like they've been cut.
right. Yeah, it's basically just two air masses pushing against each other. Like the clouds are forming in one, and then there's another air mass which is a different temperature, and then you get
Oh, by the way, thanks for this. Is awesome. This is really cool.
yeah.
I'm looking at the animation along the border with Mexico.
Yeah, you can see like yeah, if you look off the coast there, you'll see the ripples forming in the ocean there.
Right. Yeah.
You
Uh-huh.
can see like so it's pretty cool, and you can see it gives a lot much better view as to how these clouds form rather than the snapshot that you get
Right.
with worldview. Uh, and like if you look at the ones off the coast of Mexico, you follow the Mexican border out
Right.
past that first island, then you see some ripples, and they're kind of pointing towards that other little round island, which I'm not sure what that is, but there's a you can see the
Oh
ripples
yeah, those
pointing
ones.
towards
Yeah,
it.
I've seen those because
Yeah,
like you'll see it in the like what you
those,
have
those
wet
are
air going over an island. It'll leave a trail like a wake of a ship.
yeah, those are lee
I know that. Yeah,
waves.
that stuff.
Yeah, so
Yeah.
which
Yeah.
are gravity waves, but it's just they're greatly amplified by passing over the island. Like, but
Yeah.
the other waves are just regular. Basically, it's the air being squished and rippled.
Okay.
Yeah, so that's a fun thing. But yeah, so straight edges in clouds, that's generally, like it's a front, essentially. If you know about weather fronts, you see them on the weather, uh, and they are roughly straight lines. Yeah, they're in places. Like they're often like long curved lines, but if you look at them locally, they're actually, they're not curving that much, so they're essentially fairly straight. So on one side of that line, you've got warm air, and the other side you've got cold air, which makes the cloud formation different. And so as those fronts move around and they're pushed around by the big masses of air, you will get these straight edges in the cloud banks.
Hmm.
I don't see any
Yeah.
on there
Usually, I
today.
find this is, I'm loving this animation. It's so cool.
Oh, there's some contrails down off the bottom of Baja, which look kind of interesting.
Baja, there's usually quite a lot of activity there. I notice.
Yeah, as well
Just
as tourist
right,
traffic.
just at the top of the Sea of Cortez, it's usually pretty heavy. Uh, I find
But
in
yeah, but your viewers can't see your listeners can't see what we're looking at, so perhaps we should.
oh yeah, well, but I'll I'll be sharing this pretty soon. But it's yeah, it's good stuff. Oh, is actually a really good example of the leeward thing. I'm looking at South Georgia. Um,
Georgia, as in
and
next to Alabama.
no, South Georgia. I mean, we're from the same place. We actually know where South Georgia is. Remember, like the island with the
Oh right,
Falklands?
okay.
That
So
was the first place that. By the
there's
way, you sound like a man, or like Yorkshire. Well, you're Lancashire, right?
but yes, I was born in Yorkshire and I went to university in Manchester and lived there for a while.
Yeah, yeah,
Yeah,
okay.
so
So
there's a bunch of
cross
Georgias.
Pennines.
Yes, I drove back and forth a few times. Yeah, there's a bunch of Georgias. Like I always get confused which one people refer to. There's Georgia the state. There's Georgia the Eastern European country, and then there's South Georgia, which is one of the which island is it?
It's basically when you go Falklands and take a left at the Falklands. Basically,
Oh yeah,
it's east of the
yeah,
Falklands, about I don't know 500 miles or so.
yes. Okay, okay. Yeah,
There's oil down there or something. I don't know. But, yeah, because they had the fishermen there. Remember when they had that
yeah.
whole
That was
cult?
the first invasion, wasn't it? Yeah. Oh yeah, that's a nice kind of a straight edged cloud. Yeah, it doesn't really look like anything.
Yeah.
Anyway, but yeah, we're looking at these clouds, and there's you look at the size of the Earth. Like if you zoom back out and you look at how big it is, and then you see how many clouds there are, and then you watch the animation of the entire globe. You're bound to get some odd shapes at some point somewhere. It's just inevitable. There's if you're looking at this thing right now, there's probably like 10,000 different clouds that you could say something about, and if you play the animation, they're just changing every 15 minutes. So if you spend time looking at these images, you're going to see weird clouds.
Hmm.
You couldn't help but see them.
Yeah. Actually, speaking of weird clouds, so I've been obviously paying attention for a while. I've seen these ones that I call sort of drippy clouds. You know what I mean? You have a cloud, and I think there's actually a name for it. It got added to the Cloud Atlas.
What cloud? Sorry.
I call them drippy clouds. There's a cloud, and
Oh,
there's stuff that looks like it's coming out. It
yeah,
looks a little like when you see like a rainstorm when there's stuff coming. You see rain falling out of a cloud.
yeah.
But this stuff, it's like it's like you have a cloud in place, and this stuff sort of comes out and sort of
Uh-huh.
gets sort of blown slightly away. It looks like it's a slightly heavier thing.
Yeah, that's probably. I'm thinking you're referring to Virga, Virga.
It's one of the new Cloud Atlas ones. I actually have a name for it. I'll just look up Cloud Atlas.
There's Jellyfish Cloud is
Yeah, the jellyfish clouds.
yeah.
Yeah.
Those. I mean, it's not really a
Oh, it shows me the crappy movie, not
it,
that. I want the crappy movie. I want the WMO, World Meteorological Office. All right. Yeah.
yeah. I didn't think they were included in the new
They
names.
have
They call them.
the
See, I'm seeing one site that calls them Altocumulus castellanus, but they're really just high altitude clouds with precipitation, uh, and the precipitation evaporates or melts, evaporates before it gets to the ground. So you see these dangles of precipitation, but they're falling into regions of air which have much lower humidity. So the precipitation evaporates before
evaporates
it
before
reaches
it
the
gets there.
ground.
Okay.
The jellyfish cloud is really just a specific shape of cloud that does this type of precipitation that doesn't reach the
It reminds me of a
cloud.
Space Invader.
Yeah,
Uh,
they look pretty
kind of
weird.
edge.
Sometimes you see them form from a contrail. It's pretty rare. You see
Oh,
a long
actually,
line of them.
I'm on the new Cloud Atlas, and I'm sure you have the same thing, but I'll send you the link. Let me switch over. Yeah, there you go. Cavum, hole punch clouds.
Yeah, whole clouds. Yeah, there's
Those ones.
I didn't
I
think.
came across this popular mechanics article from I don't know, 50. They're talking about like Vonnegut's work with GE back in the 50s or
Uh-huh.
60s,
Cloud seeding.
and they showed that one where they can do that with a dry ice.
Yeah. Yeah, well, you could make a whole punch cloud with dry ice. I mean,
And I
really,
think, and I think, isn't the official line on the hole punch clouds it's a plane flying through them? That makes it
yes.
happen.
Generally, it almost always would seem to be a plane flying through them. But the hole punch clouds, the one you saw, I think, in the black and white picture of like the long, like kind of it leaves a long a row in the clouds. That's a much thicker cloud layer than a hole punch clouds normally form in. They normally form in very thin layers of clouds, just a few, I don't know, tens or hundreds of feet thick. And it's kind of related to what I was talking about earlier. They're actually water clouds, and
Well,
they've
are hole clouds water clouds?
well, sorry,
Well,
I
apart
meant
from ice clouds.
they're liquid water clouds, so that they're made of actual liquid water droplets. And what happens is something causes the cloud to get disturbed, and it can be in a fairly small region, and then they kind of start transitioning into ice clouds. Uh, Something passes through them and disturbs it, or maybe something was sprayed on it. Then they start precipitating out, and you can see what's going on if you look at a hole punch cloud. You can see they have this exact same precipitation that you see beneath the jellyfish clouds. It's this long kind of tail of precipitation that just evaporates away because it doesn't reach the ground because it's falling into a region of lower humidity. But yeah, the water cloud is transitioning into an ice cloud, and the ice clumps together and it falls down because the particles are bigger. It's kind of an unusual thing, and it took people quite a long time to figure out what was going on with these clouds because you don't see them every day. But yeah, it's a cool thing. Sorry, did you have a question about that?
Oh no, so I was just thinking back to the spreading thing. So like how contrails spread now.
Yeah.
If unless it's 100% humidity, it shouldn't be able to. I mean, assuming it's above you say like 67% RHW.
Yeah,
Um, if it's not, they shouldn't be able to spread, should they?
that's correct. Yes.
Right. Okay. And you're saying there must be some condensation nuclei that are involved with you say you do,
No,
basically
well, no,
you can create a contrail without a condensation nucleus
you can. No, you you don't need a condensation nucleus because there's
if it gets
plenty.
to -40.
Well, no, there's plenty of water condensation nuclei in the jet exhaust, just like the
Well, why would it be water if it's been it's just like it's a hot gas coming out? It's not water.
all right, the by water condensation nuclei, what I mean are condensation nuclei like little particles of things like soot or
Right.
things like that on which water will condense. So
Okay. Those are the
yeah,
seeds. So the soot would be the which is carbon, which would be the thing that the water from the burned fuel would attach onto, and that would be
yes.
the seed that would freeze.
Yeah, now it doesn't actually need that carbon. If there's a type of experimental plane, which I think was in the 60s or 70s, which used a hydrogen engine, and that burnt pure hydrogen with pure oxygen, and that didn't create any soot at all, and yet it still left a contrail. And the reason it left a contrail was that there is condensation, water condensation nuclei, water-friendly condensation nuclei in the air already, which is why clouds form. So you don't need that soot that's in the aircraft
Oh yeah,
exhaust.
a water droplet is a condensation nucleus as
Well,
well.
a water droplet itself is a condensation nuclei. Any water itself is a condensation site
In
for
liquid
water.
form. I mean, as gas, it isn't.
Yeah, exactly,
I mean, you
exactly.
can
I mean
have
that's
there's homogeneous and heterogeneous.
yeah,
Homogeneous means there's just water. It takes a pretty large amount of supersaturation
yeah.
before
Like you
it'll
need like
spontaneously become a water droplet. When you have a condensation nucleus, you can do it at 100%.
exactly, yeah. And then that those
And
condensation.
actually, I think with certain condensation nuclei, it can be less than 100% because like you have the like when you buy electronics, it has this old sachet which says "Do not eat." The silica stuff will draw in water vapor, even though
Yeah,
it's not 100%. So
that's
there are some
hydroscopic. I don't know actually if that actually.
it's a hydrophilic or hydros. Well, it's one of those things.
Well,
It sort of
but
absorbs.
hydroscopic it means that it absorbs it. Hydrophilic means that it likes it and
It'll
sticks to
just
it.
it'll sticks to it. Right,
Yeah.
right. Okay. Yeah.
I don't think people don't use those as condensation nuclei.
Oh no. I was just pointing out that it is possible for water can go from
I don't think that would
change
change.
from gas phase into something, or well, maybe it's absorbed as a gas. I don't know.
No,
It can be absorbed. It can be absorbed. Otherwise, they wouldn't put them in our electronics and tell us not to eat them.
yeah, well, it gets absorbed, but people don't actually use that for cloud seeding. Like
No,
there were some ideas where you could spray that stuff on hurricanes. There was a guy.
to dry them up.
It was essentially this guy had this idea. It's using the same stuff that is used in diapers or nappies, which is very very absorbent, obviously, because it needs to absorb a lot of liquid.
Yeah.
And they thought they could take that exact same stuff and spray it into hurricanes. But it would soak up the water, but it's not going to do anything in terms of making clouds or anything like that. It's not the type of thing you would use for clouds. I'm not entirely sure about the artificial snow making, like snow blowers. They add some chemicals to the water there to make snow. But I've not really looked into that.
Might be silver iodide. I know they use silver iodide in commercial cloud seeding operations.
Yeah, I mean it could be just that, but I
Yeah.
think there may be something else as well because they're spraying. They're not spraying in super cold temperatures, but yeah. So they still need ice nuclei. Actually,
Yeah.
that would still work, wouldn't it? Yeah, they don't need the that cold of a temperature, so probably it's just silver iodide. But anyway, I'd have to look
Yeah.
into that.
So another question I'd like to bring up is, as you know, I get my rainwater now analyzed, and I got it comes our rain comes in off the ocean. I'm pretty much on the coast, really.
Hmm.
How would you explain, um, apart from sloppy handling and bad reading or whatever, how when air masses from the ocean having high levels of things like aluminum, barium, strontium, um, and so on, would
Well,
that all be down to? Could it all be? I mean, if you were, for the sake of argument, to exclude user error or me just like throwing like aluminum filings in
yeah.
those samples, where could that be coming from? Would you hazard?
Well, you're not exactly on the beach when you're
No,
taking
no,
your
No. I
samples.
absolutely. I have.
You're in the city.
I'm in the city, and it's all. It's. I have. It's like a few miles of residential between me and the beach. So
Right.
of course, there's gonna be a little bit of
So
noise there.
yeah, and obviously being in a city, there's a lot of air traffic, not air traffic, sorry, a lot of road traffic. So you get a lot of, and there's a lot of houses with things
Mhm.
like furnaces and things like that. So there's a lot of pollution in the city. So you're not exactly getting like pristine air where you are. It might be interesting for you to try taking some samples by the beach to see if you get variations. But there are other factors as well.
Oh, by the way, actually, that's the thing. The other thing is that I do have such massive variation because sometimes I
Yeah.
think, oh, I'll get a lot, and then zip nada, and or the variation will go from down below 50 micrograms per liter to over 500.
Yeah, I was looking
So
looking at some of your. I just randomly picked like one of your reports off your website. There's one. Let's see, what does it say? Chiloquin Sivon? Is that's something that?
Savon, they spelled it wrong. It was snow. I got crappy writing. I have really bad. I don't know how they
Oh,
got snow to Sivon, but
really? Is that
yeah,
snow?
Sivon. Yes, let's call it Sivon. It's
Yeah,
a special snow.
and yeah,
Yeah.
it's kind of interesting the variation you're getting in that. But you got
Yeah,
things like you have a lot of iron, which
and
is
actually,
odd.
the reason I test for iron was because of David Keith's paper, because he proposed putting those little nano discs with
Yeah, but
it was.
they weren't made of iron though. They were.
Oh no, they were, because no, the disc was 50 nanometers across. There was a layer of alumina, which is aluminum oxide,
Uh huh.
or aluminium for
Yes.
the people back home, and then elemental aluminum, and then underneath that there was a layer of barium titanate, and underneath that ferrite. The ferrite was so you could
Huh.
steer it, because they wanted like you want to be able to sort of tilt it around to align it with the sun for reflection or something. And I thought, hey, if he's talking about it, I'll look for it. And sure enough, I got a huge amount of aluminum, or sorry, titanium and iron.
It's interesting because
So
I've got a picture of that disc and it doesn't
yeah,
it,
it's funky looking thing.
it
Yeah.
doesn't mention the iron though. There must be
Well,
a different,
if you
probably a
go,
different
no,
version of it.
it's magnetite. It's he calls it. There's
R-
magnetite. It's ferrous.
Right, but yeah,
Yeah.
I
So
have
that's a
pictures.
little bit at the bottom. I think there's a diagram if you can find that. Pull up that paper, the PNAS one.
Yeah, I'm just looking at like a random image that I saw
Yeah. I think
on the
it
internet.
might be on my site somewhere. So yeah,
But anyway,
that's
all
I'll
right.
look
So
out
yeah, that
for
makes
that.
sense. Though, like it seems, but yeah,
Yeah.
the thing about those discs is, if they were using that, you'd see them under a microscope because they're not that big. They're not that small. They're 10 microns across. You
Well,
know.
if they were using that, if I had a microscope, well, whatever. Because it was mentioned, I
Yeah.
thought I'd look for it.
Yeah.
I don't
But
know what specifically is being done,
right.
and the proposals. And actually, this is a good place to segue to. So, of course, there are these proposals,
Hmm.
and it's been discussed. And for people who aren't aware of this, um, it's been proposed as a possible solution for global warming to put reflective particles into the sky to reflect sunlight back into space to reduce the effect of global warming.
Yes.
And originally, there was, most of the talk was about sulfate sulfuric acid. And there's less talk of that. I mean, well, frankly, that's acid rain. It's not terribly wonderful. But there has been discussion about using, amongst other things, aluminum nanoparticles. David Keith talked about that himself. It's certainly been proposed.
I don't think
Uh,
that's true though. I think the sulfate thing is still the main thing that people are looking at.
I've also
Like
heard them like talking about calcite. That's another one. Like basically
spray.
calcite being sort of like antacid stuff.
Yeah, that doesn't sound right. There's a thing called
Yeah.
chemical weathering, which is a method of sequestering carbon dioxide using calcium carbonate. But I'm not sure if that's related. But you could.
Well, no, they were. They were actually that was one of the proposals, calcite, which I'm not
Right,
sure. I
we'll have to
mean,
check that out.
and of course, when people look up geoengineering, there's the two proposals. One is carbon dioxide removal, and the other one is solar radiation management or albedo
Yes.
mitigation. So, um, the the my research has been mostly concentrating on human health impact. So the proposed geoengineering things like aluminum, and it is actually aluminum is not really that good for you. It's been implicated with Alzheimer's and stuff, and I oh, are you still there?
Yeah. Yeah,
Oh,
absolutely.
I heard a phone. Um,
Nothing going on here.
I I um I just want to check with you that you certainly you wouldn't um condone adding more poisons into the environment.
Well, I'm against pollution of any sort.
Good. Yeah, we're on the same page on that.
But there are you gotta you gotta know what you're talking about though when you're saying like pollution. Like aluminum oxide is not something that I would consider a pollution. At worst, it's a possible irritant because aluminum oxide is sandpaper. When you sand something, you're using aluminum oxide. That's what they make it out of. So
But
it's not really a
even
pollutant.
though it's clear link to Alzheimer's, you didn't see there's a link between aluminum and Alzheimer's.
Well, there's a suggested link, and if you look at the Alzheimer's Association or the CDC or anybody like that, they will tell you that there's no actual evidence of this link. And if you think about it, soda cans are made of aluminum, cooking things are made of aluminum. Aluminum is found in deodorants. Aluminum is everywhere. The rocks around you are made of aluminum. The soil in California, in Northern California, is nearly 10% aluminum. The aluminum is everywhere. And
So
it's not like we're seeing higher rates of illnesses in Northern California versus Southern Florida because there's so much aluminum. The soil in Florida is about less than 1% aluminum. Soil in Northern California is over 10% aluminum, and it is in very small form. It's like in dust year. So when it dries and blows in the air, you're breathing in this dust that's got aluminum in it. But no one's ever discovered that people in Northern California are getting sick more than people in Florida. If anything, it's the other way around.
so would you say that if there was if there was aluminum to be found in the air,
Which
you would
there
say
is.
that
Yeah, there's
uh,
definitely aluminum flying in the air.
so that's all from ground, just like stuff blowing from the ground and it
Some
gets
of it could be from industrial
pulled up.
emissions, but the vast majority of aluminum in the air will come just basically from mineral dust, rocks. Most rocks are a class of rocks called aluminosilicates, which contains aluminum and silicon and a bunch of other things like calcium and things like that. But any rock you pick up is going to have a lot of aluminum in it. Uh,
So the
it's
so basically rocks but knocking into each other will create smaller rocks and get airborne.
the average person like eats around like 5 or 6 milligrams of aluminum every day in their food, just because it's in the plants. When the plants grow in soil, they take on some aluminum and it gets in there. You get a little bit from your soda cans, not very much because they coat it to stop that
With
happening.
the phenol A, which is nasty.
Yeah, and aluminum foil, Reynolds wrap in America. Uh, that's there's aluminum everywhere. It's not
It's in
like
vaccines. It's in
well,
underarm deodorant. It's
I
in
don't. I'm not sure it's in vaccines
oh,
exactly.
it is actually it's the adjuvant. Yeah, there's
Hmm. Well, if
so,
it is, it's
there's actually a really good there's a yeah there's plenty of research on that. But yeah,
okay.
aluminum it's not Right. I mean, it's common. We have it. We're surrounded by it. We live in an
Well,
aluminum age.
I know that there are lots of people say that aluminum is really bad for you, but there's really no good evidence that it's doing anything bad. Like, you probably look at more alternative sites than I do. So you're probably more into more like alternative health, like anti-GMO type things. But if you look at the actual evidence, it doesn't really seem like it's doing anything.
Okay, I'll do a little
But
experiment.
we'd have to agree to disagree on that one because it's a large topic. But
Well, if you go to PubMed, type in aluminum and tox, tox, toxicity or Alzheimer's, you're going to get a whole lot of literature.
right, but you're not going to get any of
But
that.
I mean, I know officially there hasn't been no, the CDC hasn't said yes, this causes that. I'm aware of that.
Right, but I think you're perhaps putting a bit more weight on it than it really deserves. Like if people like Mike Adams say that aluminum is bad for you, it's not really good evidence that aluminum is bad for you. And you can always find a few papers on some subject on PubMed because they're not really a publishing thing; they just catalog everything. So there's lots of journals that don't have very strict standards of publication, and they have pretty poor levels of acceptance. What they will accept. So I'm not really sold on the idea that aluminum is bad for you. I mean,
But they
obviously.
do. It is considered a risk factor for
Well,
aluminum
if
for
you
for Alzheimer's. No.
no, it's not. It's not. It's there's a correlation between aluminum being found in the brains of people who have Alzheimer's. That doesn't mean that they that their Alzheimer's was caused by aluminum. What's much more likely is that it's the other way around, and that their
Oh,
types of illness.
the disease makes them take it on more.
Yes, yeah, there's because of the drugs that they are given. There's types of drugs which alter the brain chemistry. Obviously, Alzheimer's is a degradation of degrading of the brain. So they have to take all these very strong drugs as you get into the later stages, which do things to your brain chemistry, and that is thought to be the reason why Alzheimer's patients get this aluminum in the brain because of the drugs that they've been taking. Again, I would have to check that, but that's as I remember it.
Well, I think that's the one we're going to disagree
Well,
on, which is
you should
fine.
you
Which
should
is fine. Well, it's we
I'd look
need
that
both
one up
sides
though.
of this. We need both sides of this.
Yeah.
Um, but yeah, aluminum's not good. Personally, I try to. I mean, I cook in. It's until you know how safe stuff is. It's best
Well, we
with
do,
aluminum.
but we do know how safe aluminum is. It's been used for like a century since aluminum became cheap enough to use in everything, and we use it in
Uh,
cookware and.
I don't.
Well, yeah, you don't, but I do, and I'm fine. Nothing wrong
Oh,
with my brain.
yeah.
Uh,
All right. Well,
I just wanted to talk about something very briefly
oh, please.
on your snow sample, your Chiloquin
My
snow.
Sivan.
Yes,
Right, I have a look.
the you mentioned, I think, in the discussion something about the reporting limit.
Oh, right, yeah, yeah. So reporting limit, there's reporting limit and method detection limit are two different
Uh-huh.
things.
But it's
Method detection limit is what the machine is able to find, and the reporting limit's above that.
right,
And
but
it's not and I haven't said that I don't know at what level these things are toxic. You don't know how much,
yeah.
uranium is toxic. You don't know how much water is
But I
toxic.
think I think the post you made on that thing, it kind of seemed to imply that being higher than the reporting limit was a bad thing.
Well, my point is, why are these large and varying amounts of
But
metal
the thing is,
around?
in many cases, they're not actually large. I mean, the limit for aluminum in water is it's like 2 milligrams per liter, which is 2,000 parts per billion. But the things that you're finding in it are in the hundreds, so they're a lot lower than the actual the limit that the
This,
EPA set.
yeah, it's. I mean, with when you put water through water treatment, you'll have. I mean, groundwater can get contaminated with what's on the ground. There's stuff there's added, this fluoride and all that sort of stuff that gets added to drinking water. Plus, it can come through lead pipes and all kinds of stuff. So,
Right. So you're
water
saying
from your tap,
rainwater should be clean. Is what
water
you're
from the
saying.
tap is not the same as water falling from
All
the
right.
sky. I
So
am
then my question would be,
my concern is
how do you know
what
it's high?
what my concern is I want to find out what the condensation nuclei are
Yeah, but
and what they're made of.
these
And when you see high
tests,
levels of aluminum
how
barium
do you know
strontium,
it's high? High relative to what? What is normal rainfall?
I am. Hang on, I'm just trying to pull up my website.
Because
It's slow today.
I've got studies done back from 100 years ago where they measured the concentration of various metals in rainwater and in snow, and it came out in just basically the same types of levels that you're seeing. There's variations.
Oh,
Uh,
if you could send me those, that'd be great.
yeah,
It'd be good to get historical stuff. So yeah, where are we? So
but yeah, you're just looking at
yeah,
levels, and
yeah.
the way you put it, like saying it's 4 times the reporting limit, makes it sound like it's 4 times the danger level, and I think that confuses some people. And it's not. That's just the reporting limit is just the lowest level at which they can accurately measure it.
No, method detection limit is
No, the
lower.
method detection limit is the lowest level at which they can detect it.
Right.
Reporting limit is the lowest level at which they can measure it in terms of giving you a number as to how much there actually is, an accurate number. Below that level, they have to kind of use these statistical methods to work out what it might be. So it's pretty inaccurate. But being 5 times higher than the reporting limit
Well,
doesn't mean it's high.
the other convenient thing about reporting limit is because since the reporting limit, like for aluminum, is 50 and titanium is 0.5, if you just give the bare numbers, like the titanium would seem smaller than aluminum.
No, but that doesn't mean anything. That just means how good the test is at detecting those things. It means it's a lot harder for the test to detect aluminum than it is to detect titanium, because titanium has a much more unique spectrographic signature, so they can detect much smaller amounts of it. But aluminum's kind of a dull molecule, so you have to have a lot more of it to be able to detect it. So these reporting limits don't mean anything. They don't mean anything about how much there actually is there. They just mean something about how well the test works.
I am reporting how much there is, and the fact that there's this vast variation, like
right.
like here,
the reporting limits. You shouldn't
titanium.
use that as anything because it doesn't mean anything.
I'm showing the variation.
Yeah, but the variation in the reporting limit doesn't mean anything. So you're saying what things are relative to the reporting limit.
The reporting limit is fixed. For aluminum, it's 50. For titanium, it's 0.5.
Right.
I am showing how.
But say something was 10 times what the reporting limit was. That would be completely different and arbitrary.
It's a unit. I'm using it as a unit.
But you can't. You can't use it as a unit because it doesn't mean anything. It just means how good the test is. All you're doing is telling people how good the test is. You're not telling them anything about how much there actually is, or how much there should be, or how much there is relative to what there should be.
But you're comparing apples to oranges. I mean, you're talking about drinking water, and I'm talking about the amount of
I'm talking about
in the sky.
I'm talking about you're using the reporting limit as a unit. You can't use it as a unit. You can't. You shouldn't even mention the reporting limit because it's just confusing people. They think the reporting limit is the limit at which you have to report it. So if you're saying something,
I think we're going to disagree on that.
Well, if you can give a good explanation as to why saying something is 5 times the reporting limit has any meaning, then I'd like to hear it.
Well, I'm saying that these metals shouldn't be in the rain at all, and we're getting
that's a different thing, though.
We're getting wildly different amounts of it, and I'm using that's just that's how I explain it basically.
All right, but it's not a useful measure, the reporting limit. So I would recommend if you want your criticism of these levels to be taken seriously, you just focus on what the actual amount is and then some actual limits, such as an EPA limit for that.
That's for drinking water. That's not for
Right. Well,
rainwater.
something like, for example, the historical levels of these things from the older tests. Like,
Yeah. Did you see
and
that one I have from Italy? There's
no, I
one
don't think
where
so.
I'll see. I think I'll send you a. I got so many freaking things. It came in like 15,000. Oh, here we go. Yeah, it was like 15,430 micrograms per liter there of aluminum, 850 micrograms per liter. That was in Perugia, Italy on June 19th, 2015. I'll send you this link. Location. Yeah, it's the variation's the big thing, really, for me.
Yeah, but
And the fact that, and also, if these proposals that I believe have been implemented, um, these are toxic metals, and they're very small. If we're to believe what they say, that like nano size bits of metal, and these are highly bioavailable, and they're not good. So I sent you.
well, I'm kind of with you about like the problems of the geoengineering proposals in terms of like health effects and things like that. These are things that need to be talked about. Where I think you've kind of jumped the gun is in thinking you have evidence that these programs are already in place. You're seeing variations in levels, but when people have done tests in the past, they also find variations in the levels. I'll send you a link to the thread.
Yeah,
I've
please.
got more.
That'd be good. You'd say that these metals aren't in there? I mean, would you say that this is down to user error, or they're not in there?
I think there's a variety of reasons, but mostly there's.
So you wouldn't say. So you would say like the cirrus clouds aren't like they don't have like metal in them.
Nothing suspicious in terms of metal. There is metal in the atmosphere, of course, from pollution.
So, but the condensation nuclei that do cause the cirrus and stuff, you'd say those are it's like mostly soot and whatnot.
Cirrus, yes, cirrus don't form on soot, I think, but I think the pollution in the air has changed the cloud cover a bit over the last 100 years. It's gone up and down. We actually used to have more pollution, so things have changed with the Clean Air Act. So there is an effect from anthropogenic condensation nuclei sources, yes.
So since the Clean Air Act, the air should have been getting cleaner then.
Yeah, it has. And there's a thing, there's a phenomenon called global dimming.
I'm aware of that, yeah.
Which basically completely turned around after the Clean Air Acts were implemented. It's kind of slightly on the upswing in the last couple of years because of developing nations like China and India, but there were some classic papers on global dimming and things like pan evaporation rates.
Because I remember seeing BBC did a documentary on it, and they said that like after 9/11, all the planes were grounded, the temperature range went up by like a full degree.
Yeah, but the research they were talking about there with global dimming was actually based on figures which I think were going back to the mid 1980s or something. I can't remember exactly how much that was, but global dimming after the Clean Air Act went into effect, the trend was reversed.
So I mean, the pan evaporation has gone the other direction as well.
Yeah, I mean that's the same thing basically. The global dimming is usually measured by pan evaporation.
But the Clean Air Act was like in the 70s, right?
Yeah, but the effects didn't take effect until like the 1980s.
But the documentary I saw was made in the 1990s, and they were saying like there was a researcher out of Israel. I'm sure you've seen it.
Yes, yeah, but that research.
And he was saying that like the amount of insulation had dropped like 22%.
Insolation, as in the
incoming. SOL. Like radiant, sun rays hitting the planet's surface.
Yeah. All right. So I'm just looking at. I did a bunch of research into this back.
It's a really good documentary. If you can find it.
Yeah, but it's out of date though. That's the problem with it.
Yeah.
The research was up until the 1980s. From the 1950s to the 1980s, there was global dimming. After that, there was not. It's actually changed quite significantly.
So you say from the 70s, so the 70s onwards, it got better from the 80s
from the
onwards.
80s, from the 80s
Okay.
onwards,
All right.
which was
All right.
generally.
So therefore, there's if more sunlight's getting through, that means there's less tiny little cloud condensation. Because frank, like I'm a photographer, and it's oh, well, I've got this thing.
That's just a link to research in it.
The sky looks a lighter blue than it used to.
Yeah, that's an interesting thing as well. I wrote an article on that a few years ago.
Yeah.
There's actually a thing in psychology where people remember colors as being brighter than they actually are.
Well, fortunately, I'm a photographer, so I can look at actual slides.
Right, but have you actually like been out and taken a whole bunch of slides with the same film stock and the same camera?
Yes. Yes.
And you've compared them. Do you have a page like showing that comparison?
If you go to webriy.com/Burning Man, I've been shooting. That was from Burning Man 1998 to 2006. Same film, same camera, same lens.
Well, that'd be interesting. I'll look at that.
By the way, not safe for work. There might be a boob, so I'm not recommending anyone just go. Oh, there might be because people are less stressed.
I have no problems.
But yeah, because it was like this cobalt blue. I mean, of course, I'm still using the same film stock, so but you do see a change over. I think that's over 10 years. Just from
I see like your
98. But it's like 2009, I think I went digital. So forget about that. That's a different setup. Everything before then was Fujichrome Velvia rated at 40 ASA, shot with a 50mm f1.4 Nikkor lens on a f100.
Sorry, so when did you change over?
I think it was. I'd have to look. It was late. It was 2008, maybe. I forget. I was slowly kicking and screaming into the digital age on that because I just really loved. It really had this real punch, and of course, Velvia exaggerates colors.
Yeah,
but when you have to compare apples to apples, you have to look at the ones that were shot in Velvia in different years, and you can see it.
And of course, it's statistically you've got to look at quite a few shots and maybe even a few years.
Of course, and I have.
You were probably there. What was it like a couple of years ago? Like they had like a lot of like sandstorms in the desert.
Well, there was more than sandstorms, but that's a whole other story. But actually, the sandstorms are awesome, and also the spring, even though allegedly doesn't happen. When you have thin cloud and when the sun's low, it makes people look awesome.
Yeah, good lighting.
One
benefit of contrails.
Apply dust and chemtrails make you look good, or persistent contrails. But I'll check out this dimming thing. The whole purpose. I mean, going back to the rainwater thing, we will disagree on how I report them, but my point is why are we finding these toxic metals in the if they're in the rain, we're breathing them in. It's coming from the sky.
Yeah. Well, again,
that's the whole point, and the fact that there's massive variation. If it was a constant thing and the variation was only a couple of a standard deviation between them, that'd be fine. But why this giant orders of magnitude?
Well, it's partly the wind direction. How does the air mass that created the rain get formed? Did it form from wind blown from the north or the south or from over the ocean? And it's partly has it rained recently? If it hasn't rained recently and then it rains, then there's going to be a lot more pollution in the air, and the air kind of washes it out, and then the next day you'll see a lot less. So, there's lots of natural variations. And then, user error is harder to predict what will actually happen with that. But if you leave a sampling jar out for like a week or so,
Oh no, no, it's never a week. No, I'll if when it starts raining, I'll go up and I'll put clean glass bowls out on a plastic sheet
right, but
and wait.
where were those bowls beforehand?
Well, I keep them clean. I use reverse osmosis water to clean them out, and I store them facing down so no crap gets in.
Well, that means that the rim of the bowl is touching the whatever you're storing them on. So there could be stuff on the rim, and when water hits that, it rolls down. It doesn't take very much. We're talking about parts per billion here. So if you even get like a little crumb or something
Well,
on the bowl.
There we have. I'm using the same technique for all of them, and they still have massive variability. That's all I'm saying.
You should maybe try doing like some kind of control where you take a bowl. Always take two bowls and like randomly pick one. Take one, stick it outside, and take the other one and put it like outside, but say underneath a plastic, an upside down plastic box or something, so it doesn't get anything in. And then fill it with the same amount of water as the other bowl did, like from a bottle, and then test both samples. That would be like a way of trying to eliminate or identify any kind of user error. I mean, it's probably getting a little bit too much work.
It would be difficult because like I said, the window's pretty short because it's like when it starts raining, and because when it starts raining, I want to collect.
Yeah. Well,
you don't wait till the next day when it's been like right now it's been raining for whatever, so whatever it's been in the atmosphere will be already mostly washed out.
I mean, there could be even things like whatever's on your hands. If you've been handling something and then your thumb is on the inside of the bowl.
I'm not putting my hands in it.
Yeah, but like when you pick up the bowl, do you pick it up? Do you ever touch the inside of the bowl? Like it's.
No, it's a big glass.
Yeah, but there's lots because we're talking about such small amounts of these things. Yeah. Like a little bit of something falling into the bowl from somewhere, like from you or from something else, and then I take it you're pouring it from the bowl into something else. You probably have to pour it into a jug first before you poured it into a small bottle.
I have I also have a glass
a Pyrex jug.
Pyrex. Sorry.
Yeah, I mean you got to keep that clean as well.
And that gets stored the same way.
Yeah.
And then it goes into the HP. What's HP? Whatever, the plastic bottle with the buffered with the HNO3.
Mm-hmm.
Lab. They're good lab. Campbell.
Yeah, well, all the labs, they'll give you reasonably accurate results, and you're going to find these metals in the air and hence in the rain. But I don't.
So what other sources? What other sources of metal in the air would there be? So like cars and industry and stuff. So where else would there be any naturally occurring?
Yeah, well,
sources of elemental metal, not oxides, not minerals, but actual metal itself.
You're not actually measuring elemental metal though. The tests that you do don't actually.
Well, of
measure...
course. I mean that's a total amount of metal. So that includes metal salts.
Yeah, just aluminum oxide or rock.
Or like unoxidized elemental metal shouldn't be in the atmosphere at all.
Well, no, you're going to get some because you're like just friction and stuff like that will, like from brake pads, you get the metal on the brake pads like wearing off. That's actually quite a big source of pollution next to some roads. The brake pad linings, and various other forms of things like construction when building things. You're going to get bits of metal, but elemental metal. I don't know if there's really that much of that in the air because it tends to break down in nature, so you don't get very much.
I know aluminum's very reactive. It's hard to keep aluminum not oxidized. As soon as you scratch it,
it hardly occurs at all in its metallic form in nature. You have to kind of crack it out of the rocks using this quite energy intensive process.
Takes a lot of power.
Yeah, but it's still it's still cheaper than digging up other things. Uh, but yeah, my answer there was that I don't think there will be very much in terms of elemental metals in the air. I don't really know, but the tests you're doing don't actually show elemental metals, and none of the other tests that
Oh
anyone
no, no,
else is doing.
I don't claim to either. I
Yeah,
mean, it's just like,
Dane Wigington does though. He claims that they're measuring elemental metal when
well, I don't
it's
speak for
not.
anyone but myself. So.
His test very specifically doesn't measure that.
Yeah, because basically what happens is when you, so for anyone who wants to do this, when you send a sample to a lab, it's dissolved in an acid, and that's how they separate out the metals. They know the total amount of metal from elemental metal to like salt is sodium and chloride. So if you put salt in a thing, it'll say, oh yeah, there's this much sodium in it.
Well, that's when they're doing very specific tests. So I don't think that's how your lab is actually testing for the metals. They're probably using plasma spectrography.
I forget the name of the gizmo. I went to see it. I'll get back to it. But they could give you they search for different metals, but it is actually broken down and includes the metals that have been bound to other elements in
Yeah,
salts.
yeah, but the tests, I'm not entirely
So like
sure.
rust, like if you want to know how much like if you gave them rust, they would say, oh, there's this much iron in it.
Yeah,
That's another way of explaining it. That's rust
again,
being
I
iron
think
oxide.
the way these tests normally work is that they heat up the sample, they dissolve it first into some kind of carrier, and then they heat it up so it turns into a plasma, which actually strips things down into its actual atoms rather than the compounds, and then they shine a light through it to laser through it, and then they measure the spectrum,
Yeah, mass
the
spectrography.
absorption spectrum. So
Spectrography.
yeah,
How do you say that? I've always like
I don't know.
spectrography.
Not going to get me to try that now.
No matter which way you say it, it sounds wrong.
Spectrography.
Spectrography.
I
Yeah.
don't know. I can't even talk now. So yeah, but yeah, that test doesn't actually show like the individual things. Like the one you mentioned with the dissolving in an acid, I'm not sure, but I think that might be just for very specific types of things, rather than because the spectrography one measures all of metals basically at the same time. But yeah, I'd have to check on that one. But either way, you're not
Yeah.
measuring individual metals.
When I was a kid, we did like titration and like all colored things.
Yeah, yeah.
We didn't have fancy
I got
machines.
my O level in chemistry, just like you.
Yeah. Yeah, I did physics, chemistry, biology, O level, and some other stuff. Even actually, I have an astronomy O level as well. That's kind of cool. Into things like Cepheid clusters and Cepheid variables, all that cool stuff.
All right, so
Yeah. Anyway, well, thank you so much for coming on.
you're very
I'm
welcome.
talking as if this is like some freaking studio. But like I said, I wanted to, shake hands kind of thing. Like, oh hi, we both know where we each other stand, and we have very different ideas about the same thing. I think we would hopefully both agree that it would something we would not want to see happen because we don't know about the health impacts. Would I be right? I don't want to speak
Yeah,
for
well,
you.
I think it's like most geoengineering researchers think it's not a very good idea. Like David Keith would very much prefer to actually reduce carbon emissions. In fact, he's doing work in carbon capture. The reason most people are doing this work in geoengineering research is just in case. And part of that
a
is
last resort.
well, it's not even that. It's just in case like China decides to do it, or if Russia decides to do it. Like if we have the science, we can persuade them that it's a bad idea if we can figure out whether it's a bad idea or not. I think it's pretty unlikely that the U.S. government is going to do anything anytime soon. The Republicans in America like the idea because it lets them off the hook for doing any kind of carbon reduction. So it's economically a good idea. So the fiscal conservatives like it, but long term, I don't really see it happening. Not within the next 10 years at least. I would say probably,
Well,
hopefully, never. I would.
well, I know, like David Keith, they're talking about doing a limited experiment, I think, from a balloon or something. Or...
Yeah, but the talk, the amount they're talking about spraying is about, I think, 5 kilograms,
Mm.
which is 14 pounds or whatever.
Actually, wasn't the Operation Popeye used less than that? I believe it was only a few pounds for the entire operation.
Well, Popeye was a cloud seeding operation,
Yeah, but it doesn't take very much.
but that's a completely different type of thing. Though we're talking
Oh
about.
no, yeah, I mean, yeah, one solar radiation management, the other one is like precipitation enhancement. I know.
Yeah,
You can achieve a lot with a small
no,
amount
you
if
can't.
if
No,
the particle size is small enough.
no, not really. You can make
Oh, sure. Oh, wait.
cloud do
I
something.
will have to take issue with this. So, um, the smaller the particle size, the more condensation nuclei you have.
Right.
If you can get stuff very, very small, you get a whole lot of condensation nuclei with a pretty
That's true.
small mass.
But we're talking about solar radiation management.
Yeah, when the condensation nuclei will attract water, and that will be the reflective thing.
Well, that's just one of the types of proposals. Like, for example,
Yeah,
the shiny disk thing that you mentioned earlier is completely different to that, and
yeah,
the aluminum oxide thing is different to that again.
yeah.
It depends what the mechanism is. Some of them is about promoting cirrus cloud formation
Mhm.
or subvisible cirrus.
Do
Uh,
you say subvisible cirrus?
yeah.
Huh. That sounds like less blue skies to me.
Well, it's actually the same blue skies. Well, it's
So subvisible. So it does. They don't stick together. It's just like it's like a vague, slightly like foggier almost.
it's there.
I haven't heard that term. Subvisible cirrus.
Yeah, it's not actually dense enough to actually interfere with the sunlight at all. There's haze, which is one step above subvisible cirrus. Subvisible cirrus is essentially invisible to the naked eye. It doesn't really change the color of the sky, but it's still, it reflects like a very small amount, like 1 or 2% or something like that.
So it'll make it milkier looking.
It doesn't really because it doesn't scatter the light in the same way.
And presumably cirrus will be high altitude, right?
Yeah, the physics of it work out so that the subvisible cirrus augmentation, as I remember, doesn't actually change the sky significantly. Like there was some research done on exactly that question, whether it would make the skies look more milky, and they did simulations of how it would scatter the light and everything, and it turned out it was a very, very small amount.
Oh, but a small amount, but
Not
some
not
amount.
physically perceptible. You wouldn't see it in photo comparisons, for example.
Oh.
They ran simulations of it. But anyway, this is all,
But
all
it would be.
hypothetical.
No, this would be a proposal. But it's a subvisible cirrus would would make it just increase the albedo a little bit, right? Is that the idea?
Yeah, but that's the albedo from the perspective of the sun.
Right.
So it's not the milkiness of the sky and the albedo aren't the exact same thing. They're different things. One is like what happens when you look up at the sky, and the other is like what happens when radiation comes down from above. If you're getting the light coming through, it's no good.
Well, if I remember, the albedo is basically the sun, like how much reflectivity. Like if it's overcast, that's high albedo. When it's clear, no albedo. Right?
Not exactly. No.
If the air is perfectly clean, if the air is perfectly clean,
Uh,
albedo is the amount of the whiteness of the sky,
right, but albedo is how white the Earth looks from satellites or from the
the
sun.
reflectivity.
Yeah, so it's not necessarily the same thing as what you see when you're looking up. Because when you're looking up, you're seeing the scattering of the atmosphere, which is related to, but not the same as, the reflective nature of the atmosphere. It's like if you're
So that's really a semantical difference.
not exactly. It's like if you were underwater and you were looking up. It's very different from being above the water and looking down because you got this shiny surface from above, but you don't. You have, but then from below you have this dimming effect of the water. So your point of position within the medium makes quite a large difference.
But in either case, the incoming solar radiation gets bounced off.
Yeah, yeah, but
so so that should you would see
no,
that
because
on the
it's
ground.
not the heat. It's not the visible radiation. It's the heat radiation.
Oh, so it's only the subvisible stuff is only infrared.
I'll send you a link that has a photo comparison between two images, one of which is both from Earth Observatory from the World View. One is the visible spectrum, the true color one, and the one below that is the cirrus detection. And you can see the true color image. You can't see that boundary between the cirrus and no cirrus because it looks exactly the same. The subvisible cirrus. And the article itself, I believe, is titled Invisible Cirrus.
Yeah, because I'm looking at the bottom one. On the bottom left, actually the center of the image down at the bottom, it looks like there's some stuff coming off the side, more in a more linear way. And
yeah, but there's regions where there's like the middle top of the image, just to the left of the middle of the top of the image. There's a clear delineation, like that third square.
Oh,
along.
right. Yeah, I got you. Sorry, yeah. I was actually looking at the shape of the actual cloud bit in the middle, how it differed around the edges. Sorry,
right.
I got.
Yeah, so the thin grey stuff you're seeing around is this invisible cirrus, this subvisible cirrus.
Yeah,
and that's the type of thing. If you could.
So what's that made of? Is that water?
Oh, it's still tiny ice particles. Yeah.
Oh.
But they're just really, really tiny.
Yeah.
So that they
the
light just goes right through them basically.
But only affects the infrared region. Huh.
So that's one factor in the radiation budgets of the Earth. The radiation going in and the radiation going out. If there's more of these subvisible cirrus clouds, then there's going to be more of some types of radiation bouncing off. And probably different types of radiation from below would get scattered in different ways. But it all just alters the radiation budget, which is quite complicated, as I'm sure you know if you've looked into geoengineering proposals. There's all different types of wavelengths and different types of cloud which interact with different wavelengths.
Yeah. More cool stuff to look into. I have to say that I'm still really jazzed with that freaking animation thing. It's so cool.
Yeah, well, you'll probably spend the next few weeks playing with it. It's a lot of fun.
And can you see the other side?
No, because it's a geostationary satellite.
Okay. So yeah, okay, all right.
It's actually over the east coast. It's goes,
right.
But there's a few other satellites that do similar things for the other parts of the world. There's the Japanese satellite Himawari 8. And then there's a Meteosat for the European satellite. I'll send you a link to that. I collected all of them on Metabunk somewhere. Where is it called? Full disk images, Metabunk. And they have different interfaces, so they're not all quite as friendly as that one.
Yeah.
But yeah, it's a lot of fun just looking at the different animations. All right. Well,
more stuff to play with. Anyway,
I sent you a link to those sources, and they're a lot of fun.
Anyway, we should do this again. I wish you all the best of luck, and even though we don't agree.
Well, I think you say we disagree on things as if it's kind of like a philosophical disagreement, and I think maybe in some instances it might be, but I think there are also areas in which we disagree when we could get things verifiably correct. Like for example, like I don't know if you still do this, but you used to call halos sundogs.
Oh no, that was a joke. That was a joke because like these incredibly rare sundogs.
Yeah, but,
because I know it's a halo.
The problem was that other people started calling them sundogs, and that it just kind of.
I'll put an explanation, but the people who calling me know the joke.
The water.
Like, oh look, an incredibly rare sundog over San Francisco. I mean, I post that. That's the thing I do daily.
I know, but you never actually post any pictures of sundogs. because they are actually pretty
Well,
rare over San Francisco.
yeah,
So
incredibly
I
rare. The actual ones, the ones with the corners. I saw actually saw one at Baker Beach uh, New Year's Day. I saw one, but not the quote unquote incredibly rare sundogs. Those
yeah,
the
but
ones I get
I
daily.
think
That's a whole other thing.
you wouldn't be taken seriously. So I think you're really muddying the water with that, though. You're saying something is incredibly rare, and then you're posting pictures of something that isn't incredibly rare. It happens all the
Well,
time.
when I first pointed them out, I was dismissed. Oh, that's just one of these like these incredibly rare sundogs. So that was the joke, and
Right.
it's an old joke, and it's maybe I will put a thing saying yeah, no, it's a halo, but
Yeah.
yeah, so yeah,
A bit like
got
things.
lost in translation there.
Right, but there are things like that. I think where if there is some kind of disagreement, like I wrote a whole post on Metabunk about how sundogs are not incredibly rare, or like how halos are not incredibly rare. Sundogs aren't even that rare, but like I think there are certain things where we can establish a baseline of what the facts actually are. Like we can, say if a certain test uses, will detect metals or not. I think that we can actually work through some of our disagreements and figure things out and try to work more from a shared knowledge base rather than just saying we disagree on everything. Because there are things like that what a
Well,
halo is.
we disagree in a fundamental thing. I maintain that it is going on. You maintain it's not. That's the big
Right.
one.
But you maintain that partly because of evidence that you think that you have. And I think we can look at that evidence.
And you maintain your side with evidence you think you have.
Not really. I actually spend most of my time pointing out where people get their evidence wrong rather than presenting evidence. It's hard to present evidence for something not existing because it's difficult to prove a negative. It's not impossible, but it's difficult. So what I do is I look at people saying things like, "Oh, there are these high levels of aluminum in rain or snow," and then I will show them that they're not actually that
And you
high.
would say, therefore, it's not coming from the sky. It could be coming from somewhere else, for example.
Well, I would say like these levels have existed for whatever, like 100 years or whatever. It's not that unusual. So yeah, I would say that. But like then it becomes like, is this just an interpretation? Is this just your own personal feeling that there shouldn't be metals in the sky, or are you basing it on actual research? I mean, you're saying like you think that there shouldn't be metals in the sky because you live close to the ocean. Is that actually true? I mean, have you actually any way of verifying that other than just kind of like that's how it seems to be to you? I mean, that's the type of thing that you should really look into.
Hmm.
What are the expected levels of aluminum or whatever in
Well, it's actually
rainwater?
it's a little difficult with the historical airborne aluminum things because they just stopped publishing that data. EPA just stopped publishing in 2002, so we've got a big gap there.
Yeah, but you can look at historical. Did I send you that link already?
So
Uh,
I'm on full screen. Like
yeah, the one that
I'm
says
being mesmerized by the globe here.
aluminum in the United States prevalence in soil and water. That link that I sent to you.
Full HD images of the Earth.
And that has historical records of aluminum. I think I've just sent you one of them. From 19.
Is this airborne or soil based or?
This was, I believe, in. That was in soil. That was soil.
Yeah.
And then I've got
Yeah,
one.
the airborne stuff is I was looking for, and like EPA stopped reporting that in 2002.
All right. I found one in 1972, Pennsylvania, air and
Yeah,
water.
if you could find
Didn't do
airborne
it.
aluminum stuff, it'd be great.
But the thing is, they don't test for airborne aluminum because they use it as basically as a reference uh, because it's so prevalent in the air.
No, but I mean, EPA were doing up until 2002, and they stopped.
Yeah, because there was no reason to do it because they're always going to find levels of aluminum because
But
it.
if I mean, we disagree on the toxicity of it, but
Uh,
if it's a toxic thing in the air, EPA's job is to keep track of toxic things
they
in
were
the air.
never testing for elemental aluminum though.
They were testing for aluminum in some form in the air up
Yeah,
until
but it
2002.
wouldn't have told them anything if people were spraying like real aluminum in the air. It's the metallic aluminum is the one that's toxic, or potentially toxic if it can get past the blood-brain barrier in nano form. But they weren't testing for that. They never tested for that.
Uh,
So saying they stopped testing for it doesn't really mean anything. It just means that they didn't see any reason to,
they
test for.
they decided to stop reporting levels of aluminum in
Yeah,
2002, as did California EPA as well.
right, because it was costing several $1 million a year to test for it, and it wasn't telling them anything because you get the same levels year after year because you're just getting rock dust basically, mineral dust.
So you'd say like you'd say like in the atmosphere there would be like pretty much no elemental aluminum or any of these sort of things.
There would be extraordinarily low amounts of it, if
Yeah.
any. The thing
How,
is,
how about other
elemental
metals?
aluminum will just oxidize almost instantly.
Yeah.
It forms a thin layer of oxide very rapidly, and if it's nano-sized, that's pretty much all of the aluminum anyway.
Yeah.
It just oxidizes rapidly. They use aluminum in rocket motors and in thermite, precisely
But
because.
but but the thing is, when it's fired, it's gonna combust and become
Yeah, yeah,
oxide.
yeah. It
Yeah.
turns into an oxide. They use it in fireworks to make white lights in sparklers. Sparklers have it. Anyway, getting a little off topic here. But yeah, my point is that I think we can actually resolve differences of science, like questions about has there been any change in the sampling of elemental aluminum? I'd say no, there isn't, because they never tested for elemental aluminum. They just tested, the same as they do now, or same as you do now, for aluminum in whatever form.
Mhm.
So, and we could, there are various other things. I could probably go through your website and find a bunch of other things that we disagree with because you're wrong.
Oh, actually, here was the thing. Did you ever figure out the difference with all the multiple rings that I was finding? There was like the image, like the halo, which had like, so it looked like it was like
Yeah, that was
sub rings in it. What were those? What do you think?
that was a multiple ring halo.
Oh,
It's
multiple.
an incredibly rare one.
An incredibly rare.
I wrote about it on Metabunk, I think.
Oh yeah, send me a link for that.
Yeah,
Yeah.
they happen under very rare conditions. Just like sundogs are fairly rare. Halos are not that rare, but you know how a halo forms,
Yeah, the refraction and stuff.
right?
So
But
hang on.
do you know specifically why you get this 22-degree halo?
Um, Hang on, I'm just looking for this thing here. Um, well, when you send light through a prism, I mean, you can light gets bent. If it gets bent enough, it'll cause a halo.
Yeah. Yeah, so essentially, like the ice crystals that form are these hexagonal columns, uh,
But
or
don't,
hexagonal
don't
plates.
were you maintaining that they all had to be aligned in a certain way as
Yes,
well?
yes, they do.
Okay, yeah,
Yeah.
okay.
So the different types of crystals will form under different atmospheric conditions. Halos are generally, I believe, off the top of my head, like horizontal ice crystals, like they settle into this horizontal state. Yeah, I'm looking at your photos here of the multiple halo. It's pretty
Kind of
rare
cool,
thing.
kind of cool looking.
Yeah.
Oh, do you like my MacGyver thing? I put a lens cap on a selfie stick.
Yeah, it's great. I see you got a
Yeah,
Nikon thing.
yeah.
Have you ever looked at the website Atmospheric Optics?
I know
It's
that one.
at
Yeah, yeah.
Optics. They give a very good explanation of all the different types
They
of
give
halo.
an explanation.
Yeah, but
Well,
it's an explanation that's
yeah, yeah, yeah.
it's things like the 22 degrees is something
Oh,
that
that I've seen their what I don't want to say anything negative about him, so I won't say
No, feel
anything.
free. I mean, because this is the type of thing that
No, no, I
is
want to keep. My
verifiable.
whole point of this was just so we can like say hi and be nice. And I
Right, right.
wanted to have you
But
say without interruption what your view was
right,
on
but
this thing, and
my
I
my
think that's important.
my view is that we can make progress in
Mhm.
communication by discussing things like this. Like you think that at optics, there some of their explanations are perhaps not correct.
I have a different opinion of them. As we have different opinions of them.
Right,
That's all.
but the refractive properties of ice are fixed. They're measurable. You could shine a laser through some ice and it would bend through a certain degrees. And we can look at ice crystals.
Same with glass. Glass, depending on the glass, will bend a certain way. But if you, depending on what lens you make of it, it'll bend a different amount. The shape of it's the refractive index plus the shape and the other impurities and all kinds of stuff. There's a lot of things that go into optics. I know
Right,
it's a super complex thing. I hated it when I was doing A-level physics. That and fluid mechanics. Ugh.
right.
Uh,
But but the
I get it. I understand this stuff.
Yeah, but what I don't get is why you have such a negative opinion of at optics.
Yeah, well, let's not get
Is
into
it
that.
something to do with the halos? Because all the halo stuff is verifiable. You can verify that these
I
halos will form with
well,
these types of ice
they
crystals.
are. Uh, we disagree. Like for example, like Metabunk and I mean, power to you. You do your thing. We do our thing. And while we're opening lines of communication here, just like during World War II, like they got out of the trenches and played football and shared schnapps and stuff.
That's World
That's
War
what
One.
that World War One, yeah. That's the spirit I'm bringing this into, and I don't
Yeah,
want
that's
to get
fine.
into
That's
name
fine.
calling or whatever. And
No, that's fine. I
why
was,
I disagree with them is like, let's not get into that. It's divisive, and
but
I
the
don't
thing
want to be
is, the
divisive.
the division is the problem here. Like, yeah, you have one point of view, I have a different point of view. But again, it's not like I'm a liberal and you're a conservative. It's we're disagreeing on fundamental like issues of science. Like you're saying that there's something dubious about the way these halos are forming,
Mhm.
and I'm saying that there isn't, and that is something I think that we can resolve. I think.
Well, for another time, for
All
another
right,
time,
all right.
another time. But I do want to thank you for taking your time out
Yeah. Well, thank you for a polite conversation.
to
It was.
and I'm all about being nice. I mean, we can disagree, we can, vote different, we can, decide which side of the Pennines is better. I think they're both pretty cool.
Well, I'm a Yorkshireman.
Um, uh, actually, I was a newspaper reporter in Ormskirk
Yeah.
on one side of the Pennines, and I studied in Sheffield on the other. So yeah, got a bit of and I think I've kept. I mean, of course, I'm a mutt where my accent comes, but I think I still got a little bit of Northern England buried amongst the Irish in there somewhere. Can you hear any?
It sounds pretty Irish to me, but I've been
Oh,
away
okay,
for a
yeah,
while, so.
yeah. Mind you, actually, do you ever get someone say, "Oh, you sound European"?
Usually Australian.
I get Australian a lot, but I was dumbfounded when someone first when I went to college in Cardiff and when I was doing physics and when someone said, "Oh, you have an Irish accent," I'm like, which Irish accent? There's a lot of them. But but when I came here and it was broadened to all of Europe, that's like wow.
Yeah,
But I think I've over time you lose the ear for the different
you do.
regions. I
You
mean,
do.
you sounded. I was thinking Manchester.
Well, yeah, I lived there for 6 or 7 years, so
So when did you come to the
5 years.
States? I've been here since '94.
About the same, actually.
Yeah,
Yeah, I
yeah,
think it was 94.
yeah,
1983, maybe. 90,
yeah,
yeah,
yeah.
so a long time.
Yeah. I don't feel American yet.
Well,
I feel
I assume you're a
no.
citizen.
No, I'm still on a green card. I just renew my green card every however
Uh,
many years. It's a rip. It's like, ugh. I mean, The one reason I'd like to get citizenship is for jury duty, because that fascinates me. It's like, why would you want to get called for jury duty? Well, kind of cool, to
Yeah, yeah.
see how the sausage is made from the inside.
It's pretty rare to get. I get my summons all the time, but I've never actually been on a jury.
Oh, never? Well, how come? Do you go and they just say, no
I don't even go. They have you call in to this automated system. I guess I'm just being lucky, and they do like 5 times as many people as they need, just so they have enough.
Yeah.
So, all right. Well, I gotta go. It's 5:00. All
right, and thanks so much. And we'll be in touch.
Thank you, Patrick.
See you on the internet.
Indeed.
All right. Thanks so much. All right. Take it away.